There is a particle drifting through the universe right now that should not exist. Not in any dangerous sense, not in any way that threatens the stars or bends the fabric of space, but in a quieter, more unsettling way. It exists, it has always existed, and no one who first discovered it understood why. Roughly 10,000 of these particles pass through every square centimeter of your body every minute. They are passing through you now, as you read this, as you breathe, as you drift toward sleep. They arrive from space, from collisions in the upper atmosphere, from the remnants of distant supernovae. Cosmic messengers that have traveled unimaginable distances only to pass through you without leaving a trace, vanishing into the ground beneath you as if you were not there at all. You have never felt one. You will never see one. But they are real, they are constant, and they have been moving through the world since long before there were any eyes to notice them. They are called muons. And their story, the story of why they exist, what they are, and what their behavior in the heart of a giant magnetic ring in Illinois is telling us about the deepest structure of the universe, is one of the most remarkable and quietly dramatic stories in modern science. Tonight, on Valorin, we are going to follow that story from its beginning. Welcome back to Valorin Sleepy Space Mysteries. If you have been here before, you know this is a place for the long questions, the slow questions, the ones that do not have easy answers and probably do not need to be rushed. Tonight we are going to follow the muon, this strange, uninvited particle, from its accidental discovery in a cascade of cosmic debris in 1936 all the way to the center of the most closely watched experiment in modern physics. An experiment that has been quietly, patiently measuring the magnetic heartbeat of something smaller than an atom, and finding, in the 9th decimal place of a number most people have never heard of, a whisper that might just rewrite everything. If you enjoy drifting through the deep mysteries of the cosmos like this, there is another Valorin video that pairs beautifully with tonight's journey, our exploration of dark matter and the invisible architecture of galaxies. The muon, as you will come to understand, may be connected to that darkness in ways that no one yet fully comprehends. You will find it waiting on the channel. If this is your first time here, welcome. Settle in. Get comfortable. Turn off the lights if you like. This is a story that rewards stillness. And if you want to be here for all of them, for every quiet mystery we unravel together, please subscribe and turn on notifications so you never miss one. A like means more than you might imagine. And if you ever want to go deeper, our membership is always open. As for tonight, where are you watching from? Somewhere under the same stars that are, right now, raining muons down upon you. Yes, even now, even as you rest, the universe is always speaking. We are only just learning to listen. To understand why the muon matters so much, we have to begin somewhere that might seem far away from a single spinning particle. We have to begin with the question that has haunted human thought for as long as there have been humans to think it. What is the universe made of? Not in the grand philosophical sense, not what is its meaning, not what is its purpose, but in the most literal, material sense. If you could take everything you have ever touched, ever seen, ever tasted or breathed or loved, and reduce it to its most fundamental pieces, what would you find at the bottom? What are the actual ingredients of reality? For thousands of years, the answers to this question were beautiful and wrong. Ancient philosophers built systems of 4 elements, earth, water, fire, air, that felt intuitively correct for centuries but explained almost nothing on closer examination. Medieval alchemists tried to transform one substance into another, intuiting that there were shared building blocks beneath the surface of things, but never finding the right language to describe what they were looking for. It was not until the late 1700s and early 1800s that chemistry began to reveal the true architecture of matter. Not 4 elements but dozens, each with its own unique properties and atomic structure. By 1869, the Russian chemist Dmitry Mendeleev had organized these elements into the periodic table, a map so elegant that it predicted the existence of elements not yet discovered, described only by the blank spaces it left behind. The table revealed patterns. Elements in the same column behaved similarly. Gaps in the table predicted elements waiting to be found. And when those elements were eventually found, they had exactly the properties the table had implied. It was a stunning triumph, a moment when the apparent chaos of the material world revealed hidden order. But it raised a deeper question. Why were there so many elements, and why did they have the properties they did? The periodic table organized the elements beautifully, but it did not explain them. It was a map, not a theory. Told you what was there, but not why. The answers came in the early 20th century, in a cascade of discoveries that reshaped what it meant to understand the physical world. In 1897, J.J. Thomson discovered the electron, the first proof that atoms were not the indivisible endpoint of matter but had internal structure, smaller things moving inside them. In 1911, Ernest Rutherford fired particles at a sheet of gold foil and found that most of the atom was empty space, with a tiny, impossibly dense nucleus at its heart. By the 1930s, that nucleus had been resolved into 2 types of particles, protons and neutrons, and the dream of a simple, complete picture of matter seemed almost within reach. 3 particles: proton, neutron, electron. From these 3, you could build every element on the periodic table. From every element, every molecule. From every molecule, every substance in the universe: water, steel, wood, bone, starlight, memory. It was elegant, it was satisfying, and it lasted almost no time at all before the universe complicated it. By the middle of the 20th century, particle accelerators, machines that smash particles together at enormous speeds and examine the wreckage, were revealing a zoo of new subatomic particles. Pions, kaons, sigma particles, omega particles, lambda particles, dozens of exotic objects with strange names and stranger properties, all appearing in the debris of collisions and decays. The physicist Willis Lamb, accepting a Nobel Prize in 1955, reportedly joked that a new particle discovery used to earn a Nobel Prize. Now it should come with a $10,000 fine. The joke captured real frustration. Instead of finding simplicity at the bottom of reality, physicists seem to be finding an ever-growing catalog of complexity. It took decades of effort by hundreds of theorists and experimenters across multiple countries to sort through the chaos and build something coherent. What they eventually constructed over the course of the 1960s and 1970s was the most successful scientific theory in human history. They called it the Standard Model of Particle Physics. At its heart, the Standard Model says the universe is made of 12 fundamental particles of matter, organized into 2 families. The first family is the quarks: up, down, charm, strange, top, and bottom. Quarks combine in groups to form the particles inside atomic nuclei. A proton is 2 up quarks and 1 down quark. A neutron is one up quark and two down quarks. The second family is the leptons. The electron neutrino, the muon neutrino, the tau, and the tau neutrino. These 12 particles are organized into 3 generations. The first generation contains the up and down quarks, the electron and the electron neutrino, the lightest and most stable, the particles that build all ordinary matter you can see or touch. The second generation contains the charm and strange quarks, and the muon and muon neutrino. The third generation contains the top and bottom quarks, and the tau and tau neutrino. Each generation is a heavier echo of the one before it. The muon is about 207 times heavier than the electron. The tau is about 3,490 times heavier. But aside from mass, each generation mirrors the previous one exactly. The muon behaves like the electron in every interaction. It feels the electromagnetic force, the weak force. It does not feel the strong force. It has the same electric charge, the same spin. The only thing that distinguishes it from the electron is its mass. This repetition, this threefold copying of the same basic particle types at ever-increasing mass, is one of the deepest unsolved mysteries of the Standard Model. The theory contains 3 generations. It does not explain them. They are simply there, a pattern without a known origin, a repetition without a known purpose. And it is precisely this extra mass, unexplained, unjustified, simply present, that makes the muon so useful. Alongside these 12 matter particles, the Standard Model includes force-carrying particles called bosons. The photon carries the electromagnetic force. Every time light touches your eye, every time 2 charged particles attract or repel, photons are the messengers. Gluons carry the strong nuclear force that binds quarks inside protons and neutrons. Without the strong force, no atomic nucleus heavier than hydrogen could exist, and the universe would contain nothing but isolated protons drifting through empty space. W and Z bosons carry the weak nuclear force, responsible for certain kinds of radioactive decay and for the nuclear reactions inside the Sun that sustain all life on Earth. And then there is the Higgs boson, discovered at CERN in 2012, the particle associated with the Higgs field, an invisible field that permeates all of space and gives other particles their mass. Without the Higgs field, electrons and quarks would have no mass, would travel at the speed of light, and atoms as we know them could never form. 17 particles in total. And from their interactions you can derive essentially all of chemistry, all of nuclear physics, all of the behavior of electricity and magnetism and light. The Standard Model's predictive power borders on the uncanny. It calculated the magnetic behavior of the electron to more than 10 decimal places, and when experimentalists measured it, they agreed to more than 10 decimal places. That is like predicting the distance between 2 cities separated by tens of millions of miles and getting the answer right to within a dozen miles. The Standard Model predicted the existence and mass of the W and Z bosons before they were found. When they appeared at CERN in 1983, their masses matched. Predicted the top quark, found at Fermilab in 1995, the mass matched. It predicted a range for the Higgs boson's mass. Discovered in 2012, it fell exactly within that range. For more than 50 years, every test thrown at the Standard Model has come back with the same answer. Correct. And yet physicists have always known the Standard Model is not the final word. It does not include gravity, the force that shapes galaxies and holds you to the ground. General relativity, Einstein's theory of gravity, works beautifully on large scales. The Standard Model works beautifully on small scales. But combining them into a single unified theory remains one of the great unsolved problems in physics. The Standard Model does not explain dark matter, the invisible substance that makes up roughly a quarter of the universe's total mass energy, whose gravitational pull keeps galaxies from flying apart. Something massive and invisible is holding galaxies together, and the Standard Model has no particle that could account for it. It does not explain dark energy, the even more mysterious force accelerating the expansion of the universe. It does not explain why there is more matter than antimatter in the cosmos, a question whose different answer would mean nothing in the universe would exist at all, that the Big Bang's production of equal amounts of matter and antimatter would have led to total mutual annihilation, leaving behind nothing but light. The Standard Model is a palace of extraordinary beauty and precision, but several of its rooms are clearly unfinished, and a few doors open onto nothing but darkness. For decades, physicists have been searching for a crack in the palace walls. One of the most promising places they have been looking with growing intensity is a tiny property of that strange uninvited particle from 1936, the muon's magnetic moment. And what they have found there, hidden in the 9th decimal place of a number most people have never encountered, is a whisper that refuses to go away. The complication that set the whole story in motion arrived from the sky. In the 1930s, physicists began studying cosmic rays, streams of high-energy particles raining down from space, the echoes of violent events in distant galaxies, supernovae, and the hearts of quasars. These rays struck the upper atmosphere and shattered into cascades of secondary particles that fell toward the ground in showers of subatomic debris. It was in one of these showers, in 1936, that Carl Anderson and Seth Nettermeyer found something that did not belong. A particle with the electric charge of an electron but with a mass about 207 times greater. It moved through matter almost untouched, like a ghost passing through walls. It lived for roughly 2 microseconds, barely a heartbeat in any frame of reference most of us can imagine, and then it decayed, dissolving into an electron and 2 neutrinos, leaving almost no trace. Some physicists initially hoped this new particle might be the one predicted by the Japanese theorist Hideki Yukawa, who had proposed a medium-mass particle as the carrier of the strong nuclear force. But experiments soon showed that the muon did not interact strongly with atomic nuclei the way a strong force carrier should. Passed through matter too easily. It was something else entirely. Something unexpected. Something no one had asked for. The physicist Isidor Isaac Rabi captured the bewilderment with a question that has echoed through physics ever since. Who ordered that? It was funny and it was honest and it was a genuine scientific crisis. The muon did not fit. It did not belong. It was a heavier copy of the electron serving no apparent purpose in the grand machinery of matter. And nearly 90 years later, the question of why it exists remains one of the deepest open puzzles in fundamental physics. The story of the Standard Model's construction is also, in a quieter way, the story of scientific community. The dozens of exotic particles discovered in the 1950s and 1960s, the so-called particle zoo, were produced by facilities in the United States, the Soviet Union, Europe, and Japan. Physicists from countries that were geopolitical adversaries sat together at conferences and shared data and argued about interpretation. The theory that emerged from that effort, the Standard Model, was not the product of any single mind or any single nation. It was built in pieces. Murray Gell-Mann and George Zweig proposed quarks in 1964. Sheldon Glashow, Abdus Salam, and Steven Weinberg unified the electromagnetic and weak forces in the late 1960s and early 1970s. Gerard Hooft and Martinus Veltman showed the theory was mathematically consistent in a way that had been uncertain. David Politzer, David Gross, and Frank Wilczek discovered asymptotic freedom, the property of the strong force that makes quarks behave almost freely at high energies while binding tightly at low energies. Each piece was contributed by a different person, often in a different country, often building on work done by people they had never met. The Standard Model is, in this sense, one of humanity's most genuinely collaborative intellectual achievements. And the muon, that uninvited, mysterious particle that Robbie could not account for, sits inside it, organized and cataloged and assigned to the second generation of leptons, its mass unexplained but its behavior fully described. Described well enough, in fact, to predict its anomalous magnetic moment to extraordinary precision. Except, as it turns out, not quite precisely enough. The question of why the muon is heavier than the electron is not a trivial one. In the Standard Model, particle masses are not predicted from first principles. They are free parameters, numbers that have to be measured experimentally and plugged in by hand. The Standard Model does not tell you why the electron has the mass it does. It does not tell you why the muon is 207 times heavier. It does not tell you why nature repeats the lepton pattern 3 times at 3 different mass scales. These are among the approximately 19 free parameters of the Standard Model, numbers the theory requires but does not explain. A deeper theory, a more complete theory, would presumably predict these numbers from some underlying principle. Until such a theory is found, the muon's mass remains exactly what it has always been since 1936. A clue without a clear destination. A number that is precisely known and completely unexplained. And it is this unexplained mass, this extra weight that nobody ordered, that makes the muon so sensitive to new physics. Because in quantum field theory, sensitivity scales with mass squared. The heavier the particle, the more loudly it hears the whispers of the quantum vacuum. The muon, sitting 207 times heavier than the electron, hears things the electron cannot. Every charged particle that spins acts like a tiny magnet. This is not a metaphor, it is a precise physical fact. The electron, the proton, the muon, each one generates a magnetic field as a consequence of its charge and its spin, the quantum mechanical property that behaves something like rotation. Physicists describe the strength of this magnetic field using a number called the magnetic moment. And for a fundamental particle with spin 1/2, like the electron or the muon, the basic equations of quantum mechanics predict that the magnetic moment should have a specific value, characterized by a number called g, which the simplest calculation gives as exactly 2. But quantum mechanics, even in its simplest form, is never truly simple. Because the vacuum of space, the apparent emptiness between particles, is not empty at all. It seethes. It boils. Pairs of virtual particles flicker into existence and annihilate each other, borrowing energy from the uncertainty principle for intervals so short they barely leave a trace. Virtual photons, virtual electrons, virtual quarks, virtual W and Z bosons. Every particle in the Standard Model participates in this quantum foam, popping in and out of existence in the space around real particles. And when a muon sits in a magnetic field, all of these fleeting virtual particles interact with it. They tug at its magnetic moment, shifting it away from the basic prediction of exactly 2. The total shift is called the anomalous magnetic moment, written as a small letter a, defined as g-2, divided by 2. For the muon, this number is approximately 0.0011659. It does not look dramatic. It is barely more than 0.1% above zero. But this tiny number is extraordinarily rich with information. Every particle in the Standard Model contributes to the anomalous magnetic moment. Every force, every interaction, every type of virtual particle flickering in the quantum vacuum around the muon leaves its fingerprint on this single number. Measure the anomalous magnetic moment precisely enough, and you are, in a very real sense, taking the temperature of the entire Standard Model at once. You are asking the universe, is this your complete inventory? Have you shown us everything? The answer, if there are particles and forces beyond the Standard Model, would appear here first. Because those undiscovered particles would also create virtual pairs. They would also flicker around the muon. They would also nudge its magnetic moment, adding contributions that the Standard Model does not predict. The contribution would be small. If these particles were obvious, we would have found them already. But it would be there, hiding in the last few decimal places, waiting to be found. This is why the muon occupies such a special position in physics. Not because of its mysteriousness in isolation, but because of what its anomalous magnetic moment could reveal. The muon is a messenger, a particle that carries, encoded in the finest details of its magnetic behavior, information about whatever lies beyond the known universe of particles. And there is another reason the muon is uniquely suited for this role: its mass. In quantum field theory, the contribution of heavy virtual particles to a magnetic moment scales with the square of the measured particle's mass. The heavier you are, the more sensitive you are to heavy virtual particles lurking in the quantum vacuum. The electron is very light, nearly 2,000 times lighter than a proton. Because of this, the electron's magnetic moment is almost blind to any new heavy particles that might exist. The muon, being 207 times heavier than the electron, is roughly 43,000 times more sensitive to such heavy new physics. A discrepancy invisible to the electron could be plainly visible in the muon. And unlike the tau lepton, the third and heaviest charged lepton, more sensitive still to new physics, the muon lives long enough to study. The tau exists for only about 300 femtoseconds, far too brief for a precision measurement. The muon's lifetime of roughly 2 microseconds is, in the world of particle physics, generous. Long enough to create focus beams. Long enough to store in magnetic rings. Long enough to watch and to measure. The muon is the Goldilocks particle for this measurement. Not too light, not too short-lived, just right. To understand just how precise the theoretical prediction must be, consider what goes into the quantum electrodynamic contribution alone. At the simplest level, what physicists call the one-loop level, the muon emits a single virtual photon, which briefly exists before being reabsorbed. This process was first calculated by Julian Schwinger in 1948, and the result is a single elegant expression. The anomaly is approximately equal to the fine structure constant divided by 2 times pi. That number is roughly 0.001162, which accounts for more than 99.9% of the total anomalous magnetic moment. Schwinger's calculation was itself a landmark, one of the first successful predictions of quantum field theory. confirming that the framework was not just mathematically consistent but genuinely described the behavior of the physical world. But physics never stops at one loop. At the two-loop level, the muon can exchange two virtual photons, or a single virtual photon can briefly create a virtual electron-positron pair that annihilates back into a photon. Each of these processes contributes a smaller correction. At three loops, there are thousands of individual Feynman diagrams, mathematical pictures representing different ways the virtual particles can interact, and each diagram is a separate integral that must be evaluated. At 4 loops, there are tens of thousands. At 5 loops, the calculation performed by Toichiro Kinoshita and collaborators over decades of painstaking work, there are more than 12,000 individual diagrams. The 5-loop quantum electrodynamic contribution has been computed numerically to precision far exceeding what any experiment could test. The quantum electrodynamic sector of the calculation is, in a sense, under complete theoretical control. The electroweak contribution from virtual W bosons, Z bosons, and the Higgs boson is much smaller and also well understood. This means that 2 of the 3 forces in the standard model are contributing known, well-controlled amounts to the muon's magnetic moment. The entire uncertainty in the theoretical prediction comes from the third force, the strong force, from the hadronic contributions, from the behavior of quarks and gluons at low energies, where perturbation theory breaks down and the calculations become genuinely, fundamentally hard. The precision of the electrodynamic calculation makes the hadronic uncertainty stand out all the more starkly. You have calculated 2 parts of a 3-part sum to extraordinary accuracy, and the third part is the problem. The first attempts to measure the muon's anomalous magnetic moment began at CERN in Geneva in the late 1950s. Early experiments confirmed the basic picture of quantum electrodynamics and measured the anomalous part to a precision of a few percent. Enough to show the theory was on the right track, but not nearly enough to see anything new. Over the following 2 decades, CERN conducted increasingly sophisticated experiments, each generation improving on the last. The third CERN experiment, completed in 1979, reached 7 parts per million. Each time, the measured value agreed with the standard model prediction within experimental uncertainty. But physicists wanted to push to parts per billion, where new physics might finally be visible. That ambition gave birth to experiment E821 at Brookhaven National Laboratory on Long Island, New York. The principle behind it rested on a phenomenon called spin precession. Every muon has a spin axis, imagine a tiny gyroscope, and when placed in a magnetic field, that axis does not simply sit still. It precesses, slowly rotating around the direction of the field, like a tilted spinning top wobbling in a circle. The rate of this precession depends on the muon's magnetic moment. If G were exactly 2, the precession rate would have a precise, predictable relationship to the muon's orbital frequency in the field. But because the anomalous magnetic moment shifts G slightly above 2, there is a small difference between the precession rate and the orbital rate. Measure that difference with enough precision, and you have measured the anomaly itself. To make this measurement work, the Brookhaven team needed polarized muons, muons whose spins were preferentially aligned in one direction. These they created by slamming beams of high-energy protons into a nickel target, producing pions, unstable particles made of a quark and an antiquark, which then decayed into muons. By the laws of physics governing that decay, the muons emerged with their spins naturally aligned along their direction of motion. This was an unexpected gift from nature, an automatic polarization that made the measurement possible. The polarized muons were then injected into the centerpiece of the experiment, a superconducting ring magnet 50 feet in diameter, producing an extraordinarily uniform magnetic field. Inside this ring, the muons traveled in circles, their orbital and precession frequencies slowly diverging, the gap between them growing with every lap. That gap was the signal they were measuring. The way to detect the spin direction used a remarkable trick from the physics of the muon's decay. When a muon decays, it produces a positron along with two neutrinos. Because of the way the weak force governs this decay, the highest energy positrons tend to fly out in the direction the muon spin is pointing. By placing detectors around the inside of the storage ring and counting how many high-energy positrons arrived at each moment, the team could track how the spin direction was changing over time. The result was a pattern, an oscillating wave riding on an exponential decay, and by fitting this curve with extraordinary care, the team extracted the anomalous precession frequency, and from that, the anomalous magnetic moment. But measuring the precession frequency was only half the battle. To convert it into the anomalous magnetic moment, you also need to know the strength of the magnetic field with equal precision. The Brookhaven team used nuclear magnetic resonance probes, the same basic technology as an MRI machine in a hospital, but pushed to extraordinary levels of delicacy to map the field inside the storage ring at hundreds of positions. The field had to be uniform to within a few parts per million across the entire circumference of the ring. Any variation would cause some muons to process faster and others slower, smearing out the signal. Achieving this uniformity required painstaking adjustment of tiny iron wedges and current corrections. The field was monitored approximately every 3 days throughout data collection, building up a detailed history of how it changed over time, because temperature changes, mechanical vibrations, even the tidal pull of the moon could cause tiny shifts that had to be tracked and corrected for. When the Brookhaven experiment published its final result in 2006, it had measured the muon's anomalous magnetic moment to a precision of about half a part per million. And it found something striking. The measured value was higher than the standard model predicted, higher by about 3.3 standard deviations. 3 sigma. Tantalizing. Not proof, but a whisper that refused to go away. 3.3 sigma means the probability of that deviation arising by random statistical chance alone is about 1 in 350. That is enough to take seriously but not enough to claim a discovery. In particle physics, the conventional threshold for a discovery is 5 sigma, corresponding to a probability of about 1 in 3.5 million. The Brookhaven result was exciting, suggestive, and deeply intriguing, but it fell short of that gold standard. The physics community was electrified. Here was a real measurement from a real experiment, suggesting that the standard model might be missing something. But physicists have been burned before by signals that appeared at 3 or 4 sigma and then vanished when more data was collected. What was needed was an independent experiment, a new measurement with different equipment, different systematic effects, and more data. If the new measurement confirmed Brookhaven, the combined statistical significance would increase. If it disagreed, it would suggest the original result was a fluctuation. Either way, more data was needed, and getting more data required one of the most audacious feats of logistics in the history of experimental physics. The systematic control required by the Brookhaven experiment was itself a remarkable achievement. The storage ring magnet had to produce a field uniform to within a few parts per million across its entire 50-foot circumference. Any variation in the field would cause some muons to process faster and others slower, smearing out the oscillation signal and degrading the precision. To achieve this uniformity, the team painstakingly shimmed the magnet, adjusting tiny iron wedges and current corrections to smooth out every bump and ripple. Nuclear magnetic resonance probes mounted on a trolley that could travel around the ring measured the field at hundreds of positions, building up a detailed three-dimensional map updated approximately every 3 days throughout the data-taking period. The field was also continuously monitored between trolley runs by fixed probes stationed around the ring. Temperature changes, mechanical vibrations, seasonal ground movement, even the tidal gravitational pull of the moon and sun could shift the field by tiny but measurable amounts. Every such effect was tracked and corrected for. The electric fields used to focus the muon beam inside the ring could also affect the spin precession, but the team had a beautiful solution. They chose the muon momentum to be at a special value called the magic momentum, at which the electric field contribution to the spin precession vanishes exactly. This was not a compromise. It was an insight, a recognition that the laws of physics themselves provided a way to eliminate one of the largest potential systematic errors, if only you chose your experimental conditions carefully enough. The magic momentum is one of those moments where theoretical elegance and experimental practicality converge in a way that makes physics feel, briefly, like a gift. The muon's lifetime of roughly 2 microseconds is, in the context of this experiment, simultaneously a blessing and a challenge. It is a blessing because it is long enough to be studied, long enough to inject polarized muons into a ring, let them circulate, and watch their spins precess over many orbits before the muons decay. A particle that lasted only a nanosecond would not give you enough time. But it is a challenge because it means the muon population inside the ring is constantly shrinking. Every microsecond, a substantial fraction of the circulating muons have decayed and vanished. The signal, the oscillating count of high-energy positrons from muon decays, rides on an exponentially falling baseline. Fitting that curve accurately, extracting the precession frequency from the oscillation with minimal distortion from the exponential envelope, required sophisticated analysis techniques and careful attention to detector effects that could mimic or mask the true signal. The data analysis was carried out by multiple independent groups within the collaboration, using different methods, precisely so that any error in one group's approach would not propagate unnoticed into the final result. This kind of internal cross-checking, multiple teams analyzing the same data independently and comparing answers, is standard practice in precision physics. It is also, in its own quiet way, a demonstration of something important about how human knowledge is made. Not by single individuals arriving at solitary conclusions, but by communities of people checking each other's work. The story of spin precession and how it encodes the anomalous magnetic moment is worth dwelling on a little longer, because it is one of those moments where abstract quantum mechanics connects with concrete, measurable reality in a way that feels almost miraculous. Spin is a quantum mechanical property with no true classical analog. You cannot picture it as a tiny sphere rotating on its axis, because the analogy breaks down when you look too closely. And yet spin produces effects in the macroscopic world. It is the basis of the MRI machines in hospitals, the magnetic moments that make chemistry possible, the alignment effects that underpin everything from compass needles to hard drives. When physicists say a muon spin precesses in a magnetic field, they mean something precise. the expectation value of the spin's direction rotates around the field direction at a rate determined by the gyromagnetic ratio, and that ratio encodes in one number the cumulative effect of every virtual particle that has ever flickered around the muon in its brief existence. Measuring the precession rate is therefore not just a technical exercise. It is a way of asking the vacuum itself what it is made of. Every kind of virtual particle that can exist, every particle allowed by the laws of physics, whether we have discovered it or not, contributes something to the precession rate. The muon spin, wobbling in its magnetic field deep inside the Fermilab storage ring, is an antenna tuned to the entire universe of particles, known and unknown. The experimentalists reading the signal from that antenna are doing something that deserves to be called extraordinary. They are listening to the quantum vacuum. They are asking it, "Is this all you have?" And they are reading the answer in the timing of subatomic decays, in the energy of positrons flying into calorimeters in the dark of a particle physics detector. It is one of the most intimate conversations between human instruments and the fabric of reality that science has ever managed to arrange. That new experiment required moving the heart of the Brookhaven apparatus halfway across the United States. The central element of the muon G-2 measurement is the storage ring, the giant superconducting magnet that keeps muons circling while their spins precess. The Brookhaven ring weighed approximately 700 tons in total. Most of its iron could be disassembled and shipped by truck. But the superconducting coils, wound in a continuous loop 50 feet in diameter, could not be disassembled without being destroyed. They had to travel in one piece. A 50-foot wide structure cannot take a direct overland route from New York to Illinois. It will not fit under bridges, through tunnels around ordinary highway curves. And so the team took the long way around. In June of 2013, the ring was loaded onto a specially designed flatbed truck and driven at night. Only at night, to avoid shutting down traffic during daylight hours, to a barge waiting on Long Island. From there, the barge carried it down the Atlantic coast, around the tip of Florida, into the Gulf of Mexico, up through the Tennessee-Tombigbee waterway, and then up the Mississippi and Illinois rivers to a port near Fermilab. More than 3,200 miles of sea travel, and then back onto the flatbed truck for the final 30 miles to the laboratory, along a route that had been surveyed in advance, with utility lines raised and traffic lights temporarily removed. The ring had to remain level within a few degrees throughout the entire journey, monitored continuously by sensors. When it arrived at Fermilab on July 26, 2013, hundreds of people lined the route to watch. This massive luminous ring creeping through suburban streets in the dark, escorted by police cars, carrying within its coils years of accumulated knowledge about the behavior of particles smaller than anything visible to the naked eye. It was one of those moments when the quiet ambition of science becomes briefly, visibly extraordinary. At Fermilab, the experiment was not simply reassembled, it was transformed. The new experiment, designated E989, was a major upgrade in almost every respect. Fermilab's accelerator complex was far more powerful than Brookhaven's, allowing the production of far more muons per unit time. Where Brookhaven had accumulated roughly 4 billion decay events over its entire running period, Fermilab aimed to collect more than 20 times that. New calorimeters with better energy resolution and faster timing were installed to handle the higher event rates. New tracking systems allowed the positions of individual muons to be monitored inside the ring, providing detailed information about beam dynamics that Brookhaven had never had access to. And crucially, the entire analysis was conducted blind. The team did not know their own result until every analytical decision had been finalized, protecting against the unconscious bias that can creep into any human endeavor when you know what answer you are hoping for. Over the running period, the team installed a radio-frequency electrostatic quadrupole, a system of carefully tuned electric fields that greatly reduced the coherent oscillations of the muon beam inside the ring. This single engineering refinement reduced one of the key systematic uncertainties by a factor of 10. A factor of 10. The cumulative effect of dozens of such refinements, large and small, across years of careful work, is what brought the measurement from parts per million to parts per billion precision. The Fermilab experiment began collecting physics data in 2018. In April of 2021, it published its first result, and the result agreed almost perfectly with Brookhaven. 2 experiments, conducted at different laboratories a generation apart with different beam conditions, different detectors, and different analysis teams, arrived at essentially the same number. The discrepancy between the experimental measurement and the standard model prediction stood at approximately 4.2 sigma. The probability of that arising by chance alone was roughly 1 in 40,000. The physics community leaned forward. Over the following years, Fermilab continued collecting data through additional running periods. Each new data set confirmed the previous measurements and reduced the experimental uncertainty further. In June of 2025, the collaboration published their final result, incorporating all 6 running periods of data collected from 2018 through 2023. The precision achieved was approximately 127 parts per billion, surpassing even the experiment's original design goal. The combined world average from Brookhaven and Fermilab together reached about 124 parts per billion. The measured value of the muon's anomalous magnetic moment was 0.00116592,072, with an uncertainty of about 15 in the last 2 digits. To appreciate that number, consider this level of precision is like measuring the distance between 2 cities separated by tens of millions of miles and getting the answer right to within a dozen miles. The measurement is extraordinary, and yet the measurement is only half of the story. To know what the measurement means, you need something to compare it to. You need the standard model's prediction. And this is where the story becomes genuinely strange. Not strange in the way of new particles or exotic physics, but strange in the way of a deep and unresolved argument among some of the most capable theorists on Earth. The standard model's prediction is a sum of contributions from every particle and every force in the theory. Most of these contributions are relatively tractable. But the contribution from the strong force, from the behavior of quarks and gluons at low energies, cannot be calculated from first principles using standard techniques, because at low energies the strong force is so strong that perturbation theory breaks down completely. Physicists have developed 2 very different approaches to estimating these hadronic contributions, and the 2 approaches have been in open conflict. The first is the data-driven method, using experimental data from electron-positron collisions and a mathematical theorem called a dispersion relation to compute the hadronic vacuum polarization without ever having to solve quantum chromodynamics directly. For decades, this was the gold standard, and the consensus data-driven prediction showed the muon's measured magnetic moment running above the theoretical value by a tantalizing margin. The second approach is lattice quantum chromodynamics, discretizing spacetime into a fine grid, placing quarks and gluons on that grid, and using powerful supercomputers to simulate their interactions directly from the fundamental equations. Rigorous but computationally enormous, requiring careful control of many sources of systematic uncertainty. In 2021, a collaboration known as BMW published a landmark paper reporting a lattice calculation of the hadronic vacuum polarization with unprecedented precision. Their result was significantly larger than the data-driven value, large enough, if correct, to push the standard model prediction upward, close to the experimental measurement, and shrink the apparent discrepancy from roughly 4 sigma to essentially 0. The tantalizing hint of new physics, the result that had consumed careers and generated countless theoretical papers over 2 decades, might evaporate entirely. This created a crisis between 2 different theoretical approaches calculating the same physical quantity and arriving at significantly different answers. If the data-driven method was right, the experimental measurement disagreed with the standard model and new physics was almost certainly present. If the lattice calculation was right, the experimental measurement and the standard model agreed perfectly, and the most promising hint of new physics in a generation was a mirage. The physics community responded with intense effort. New electron-positron collision experiments at facilities in Japan, China, and Russia began delivering data on the crucial hadronic cross-sections. A collaboration in Novosibirsk published new measurements of the single most important channel for the data-driven calculation, and their result differed significantly from earlier measurements by other groups. Whether this represented a genuine discovery resolving earlier errors, or an artifact of its own systematic effects, remained unclear. In May of 2025, the Muon G-2 Theory Initiative published an updated theoretical white paper incorporating new lattice calculations. Their updated prediction was substantially higher than their 2020 value, much closer to the experimental measurement. The discrepancy had shrunk from roughly 4 sigma to somewhere between 1 and 2 sigma. The situation remains unresolved. The theoretical debate is not over. The data-driven approach and the lattice approach still disagree, and that disagreement has not been explained. The coming years, as multiple independent lattice groups refine their calculations, and new electron-positron collision data accumulates from Belle 2 in Japan and BISI in China, will be decisive. Let us imagine for a moment that the discrepancy is real, that when all the theoretical dust settles, the standard model prediction still falls short of the experimental measurement. What could be causing it? What could possibly be out there, invisible to our detectors, unknown to our textbooks, nudging the muon's magnetic moment by just this tiny amount? The most famous candidate is supersymmetry. Supersymmetry proposes a deep symmetry between the 2 types of particles in the standard model, matter particles and force carriers, such that for every matter particle there exists a bosonic partner, and for every force carrier there exists a matter partner. The electron would have a bosonic partner called the selectron. The muon would have a partner called the smuon. The photon would have a fermionic partner called the photino. In total, supersymmetry roughly doubles the number of fundamental particles. If these supersymmetric particles exist, they would create virtual pairs in the quantum vacuum around the muon, contributing to its anomalous magnetic moment. For supersymmetric particles with masses in the range of several hundred to several thousand times the proton mass, the predicted contribution is naturally in the right ballpark to explain the observed discrepancy. The theory does not need to be tuned or contorted to fit. It produces a correction of approximately the right size essentially automatically. Supersymmetry would also provide natural candidates for dark matter. The lightest supersymmetric particle, if stable, would be massive, electrically neutral, and only weakly interacting, exactly the properties required of whatever invisible substance is holding galaxies together. But the Large Hadron Collider has been searching for supersymmetric particles for more than a decade and found none. The tension between what the muon wants and what the LHC has found is real, though not impossible to reconcile with more complex versions of the theory. Other candidates exist. The dark photon is a hypothetical force-carrying particle associated with a new hidden force that interacts only very weakly with ordinary matter. If a dark photon exists with a mass and coupling strength in a certain range, it would contribute to the muon's magnetic moment in the right way, and it is independently interesting because particles in a hidden dark sector might be responsible for dark matter. The muon's magnetic moment could then be a faint echo of an entire invisible world, its behavior slightly altered by forces we have never directly detected. Leptoquarks represent another possibility, hypothetical particles that would carry both quark and lepton quantum numbers, forming a bridge between the two families of matter that the Standard Model keeps strictly separate. Some models of leptoquarks also predict effects in other measurements where small deviations from Standard Model predictions have been observed, suggesting a consistent picture rather than coincidence. Models with extraspatial dimensions, models with extended Higgs sectors featuring multiple Higgs bosons, models with composite Higgs bosons where the Higgs is not a fundamental particle but a bound state of more fundamental constituents. Each of these frameworks predicts corrections to the muon's magnetic moment of potentially the right size. And each comes with its own package of additional predictions that can be tested. The muon's anomalous magnetic moment is not an isolated measurement. It is a signpost pointing, if the discrepancy is real, toward a specific region of the landscape of possible physics beyond the Standard Model. A landscape that experimenters can then systematically explore. There is something worth reflecting on here at the edge of sleep about what the muon story actually means for the nature of science itself. The muon was discovered by accident. No one predicted it. No one asked for it. It appeared in the debris of cosmic rays in 1936, lived for 2 microseconds, and vanished. For the first years after its discovery, its existence was simply baffling. It did not fit. It did not belong. It was a heavier copy of the electron serving no apparent purpose in the grand machinery of matter. And now, nearly 90 years later, this uninvited particle has become one of the most precisely studied objects in the history of science. Hundreds of physicists across multiple continents and multiple generations have devoted careers to measuring a single property of this single particle to better than 1 part in 10 billion. They transported a 50-foot superconducting ring across the ocean and rebuilt it at a new laboratory. They mapped magnetic fields to parts per billion precision. They analyzed billions of particle decays. They controlled systematic effects at a level of precision that most people cannot even conceptualize. All of this effort, all of this ingenuity and devotion and careful painstaking work, focused on a particle nobody ordered, on a number hidden in the 9th decimal place, on a whisper so faint that distinguishing it from silence requires instruments of almost incomprehensible delicacy. The universe does not announce its secrets. It does not flash them in bright lights or broadcast them at high volume. It encodes them in the tiniest perturbations of the tiniest particles, in the faintest divergences between what we calculate and what we measure. And it takes something very specific in us, something patient, something careful, something willing to spend a lifetime listening for a signal that might not even be there, to hear them. Whether the muon's anomalous magnetic moment is telling us about new physics, or whether it is telling us only about the limits of our theoretical techniques, is a question that will be answered. The lattice calculations will improve. The electron-positron collision data will accumulate. The J-Park experiment in Japan will run, using a fundamentally different experimental technique and providing a truly independent cross-check. Independent checks will be done. The contradiction between the data-driven and lattice approaches will either be resolved or it will deepen into something undeniable. Either way, we will know more than we know now. Either way, the muon will have done its work. This strange particle that no one predicted, that lived for barely a heartbeat and decayed into electrons and neutrinos in silence, will have carried us a little further into the territory of the unknown. The universe is patient. It has been keeping its secrets for 13.8 billion years. Can wait a little longer, and so can we. The muon is still out there, raining down from the sky, passing through your body right now. Dozens of them every second, ghostly and harmless, carrying whispers from the cosmos that we are only beginning to learn how to read. Let the questions rest tonight. Let them settle like dust in the quiet dark. The measurement has been made. The calculation continues. And somewhere in the space between that extraordinary number and the theory that reaches toward it, the next revolution in physics may already be waiting, patient, invisible, and almost impossibly small. Rest now. The universe will still be speaking in the morning. It is worth pausing on what 5 sigma actually means and why physicists insist on it. In particle physics, the conventional threshold for claiming a discovery is 5 sigma, corresponding to a probability of about 1 in 3.5 million that the observed deviation could arise from random statistical fluctuation alone. This is an extremely high bar, far higher than what is used in most other scientific fields. In many areas of medical or psychological research, a result at 2 sigma, 1 in 20, is considered statistically significant. Why do particle physicists demand so much more? Because of hard experience. The history of the field is full of signals at 3 or 4 sigma that looked real, generated excitement, inspired theoretical explanations, and then evaporated when more data was collected. Every physicist working today knows stories of phantom signals. The bump at 750 giga-electron-volts that appeared in the Large Hadron Collider data in 2015 and generated over 500 theoretical papers attempting to explain it, before being revealed as a statistical fluctuation with more data. The 5 sigma threshold is not arbitrary caution. It is institutional memory. It is what happens when a field has been fooled enough times that it builds the lesson into its standards. And this is why the Muon G-2 story required so much more than a tantalizing result at 4 sigma. It required the theoretical prediction to be as solid as the experimental measurement. A crack in the palace walls means nothing if you are not sure the palace is correctly drawn. The J-Park experiment in Japan represents the next chapter of the Muon G-2 story, and its approach is radically different from Fermilab's. Rather than using muons at the magic momentum stored in a large ring, J-Park will use ultra-cold muons at almost negligibly low energies, stored in a much smaller, more compact magnetic field. The different experimental technique means entirely different systematic uncertainties. There is no overlap with the Brookhaven and Fermilab systematic error budgets. If JPark measures a value consistent with Fermilab, the experimental case will be essentially unassailable. 3 experiments, 3 different techniques, all pointing to the same number. If JPark disagrees, that will itself be a profound puzzle demanding explanation. The international dimension of the Muon G-2 story is worth noting. The experiments were conducted in the United States. The ring was built at Brookhaven, transported to Fermilab. The competing theoretical calculations came from groups in Hungary, the United Kingdom, Germany, the United States, Italy, France, and Japan. The electron-positron collision data used in the data-driven approach was collected at facilities in Russia, Italy, the United States, and Japan. The new data being collected to resolve the CMD3 tension comes from Bell 2 in Japan and BISII in China. This is, in the truest sense, a global scientific endeavor, a planet-spanning collaborative effort to measure a single property of a single particle to better than 1 part in 10 billion. Science at this level has no nationality. There is one more thing worth understanding about the theoretical side of this debate, because it illuminates something deep about how science works when it is truly hard. The data-driven method and the lattice method are not simply 2 different numerical techniques arriving at different answers. They are 2 fundamentally different philosophical approaches to the same problem. The data-driven method says, we cannot calculate hadronic vacuum polarization directly from quantum chromodynamics at low energies, because the mathematics break down. So we will use nature's own measurements, the electron-positron collision data, as a proxy. We will trust the dispersion relations that connect those measurements to what we need, because those relations are mathematically exact and model-independent. The lattice method says, we can calculate hadronic vacuum polarization directly from quantum chromodynamics, if we are willing to do the calculation numerically on a discrete grid and invest enormous computational resources. We do not need experimental proxy data. We can derive the answer from first principles just very slowly and expensively. Each method has a deep strength. The data-driven method uses real experimental measurements, which are direct glimpses of nature. The lattice method derives results from the fundamental theory itself, without relying on any other experimental input. The fact that they disagree means one of them has a problem, an uncontrolled systematic error, or a subtle flaw in the analysis, or an unrecognized source of uncertainty. Finding that problem, isolating it, and fixing it is now one of the central projects in theoretical particle physics. Some physicists have proposed using the lattice method to compute specific narrow windows of energy in the hadronic vacuum polarization and comparing those windows directly with the corresponding ranges in the electron-positron collision data. A diagnostic approach that would allow the 2 methods to be compared point by point, helping to isolate exactly where the disagreement comes from. This kind of careful, methodical diagnosis is science at its most rigorous. Not exciting in the dramatic sense. Not the kind of thing that generates news headlines or public excitement, but absolutely essential if the field is to move forward with integrity. The broader landscape of precision measurements in particle physics offers some perspective on where the Muon G-2 fits. There are other precision measurements where small deviations from standard model predictions have been observed over the years. Measurements of the decays of particles called B mesons, containing bottom quarks, have shown hints of deviations in several observables. Measurements of the W boson mass by the CDF experiment at Fermilab in 2022 showed a value significantly higher than the standard model prediction. Though subsequent measurements by other experiments have been in tension with that result, and the situation remains unclear. The anomalous magnetic moment of the muon is not alone in hinting that something might be missing from the standard model. It is one data point in a broader picture, a picture that is still being assembled, with some pieces that seem to fit together and others whose relationship is not yet clear. What gives the muon G-2 special status in this landscape is the combination of experimental precision and theoretical accessibility. The measurement is extraordinarily precise. The theoretical prediction, while contested, is at least calculable in principle, and the sources of uncertainty are understood well enough that a program exists for resolving them. This is not always the case for anomalies in particle physics. Some discrepancies exist in measurements where the theoretical calculation is so complex that uncertainty about the prediction itself dominates the picture. The muon G-2 has the virtue of clarity. The experimental measurement is solid, the theoretical challenge is well defined, and the path toward resolution. More lattice calculations, more electron-positron collision data, more independent experimental cross-checks is mapped. It will take time, but the destination is visible. The electron-positron collision data that feeds the data-driven calculation of hadronic vacuum polarization was gathered over several decades at facilities around the world. Each experiment measured the rate of hadron production at different collision energies, building up a picture of how the strong force behaves as energy varies. The data from these experiments was carefully compiled. The systematic uncertainties of each measurement were evaluated, and the contributions were stitched together into a composite picture spanning a wide energy range. This compilation process is itself a significant scientific undertaking, not as glamorous as building a storage ring or moving it across the country, but essential. Getting the input data right is as important as getting the calculation right. And it is here, in the energy range around the Rho-Meson resonance, a peak in the pion pair production rate at a collision energy of about 770 mega-electron-volts, that the most important tension in the data-driven approach currently lives. The CMD3 measurement that disagrees with earlier experiments is concentrated precisely in this energy region. The Rho-Meson resonance is not a small effect. It contributes roughly 70% of the total hadronic vacuum polarization. Getting this one region wrong means getting the whole calculation wrong. The disagreement between CMD3 and earlier measurements in this region is not a detail. It is the central unresolved question on the experimental side of the data-driven method. And until it is resolved, until new independent measurements from Bell 2 or BSI or other facilities either confirm CMD3 or confirm the earlier experiments, the data-driven prediction will carry an irreducible uncertainty that prevents it from being fully trusted. The muon story reminds us that science often advances not through the experiments we design, but through the surprises those experiments contain. Anderson and Neddermeyer were not looking for the muon. They were studying cosmic rays to understand the particles they already knew about. The muon arrived uninvited, confused everyone, and spent decades as an embarrassment to tidy theories. Today, it is the most sensitive precision probe of the quantum vacuum that experimental physics possesses. The lesson is not that accidents are the secret of science. It is that careful, disciplined observation of the natural world, pursued with patience and rigor, tends to reward you with more than you were looking for. The universe is generous with its surprises. What it asks in return is attention. The patience required to do this science is not a passive quality. It is active, disciplined, and demanding. It means returning to the same calculation year after year as computers become more powerful, reducing the lattice spacing a little more, extending the lattice volume a little more, pushing the precision a little further. It means redesigning a detector system between running periods to reduce a systematic effect that is limiting precision. It means waiting years for an accelerator upgrade that will produce more muons per second. This kind of patience is not resignation. It is strategy, the understanding that some questions can